Happy Monday, everyone. Today's video is going to be shorter. We're going to be starting 6.6. The intention is that today you'll hopefully watch this video and then also maybe watch a video or two to help you try and remember the unit circle a little bit better than we've been doing. I know different people learn different ways, so maybe somebody else's trick might be better for you. With that said, I would take some time right now, pause this video, maybe go find something for the unit circle before we move on, and I'll hopefully get you back onto this video in like 10 minutes. Alright, so the thought is that you have spent some time looking at the unit circle to try and get yourself familiar with it more, or that you at least have the unit circle in front of you right now. So 6.6 focuses on solving all trigonometric equations. And let's just try to combine trigonometric and quadratic. Trigonometric equations. It's split up in 3 sections. There's going to be 3 different videos. Today's is a lighter one, and this is just on solving by inspection. So we've looked at some simple problems before, such as sine of x is equal to a half. We know that half represents, well, sine is y over r. On a unit circle, r equals 1. So we know we are looking for the angle x. That gives us a y coordinate of a half. And for these, we're also going to need to give us a bound, because this could go forever otherwise. So I'm going to say on the boundary 0 to 2 pi, but not including 2 pi, we don't want to repeat that possible answer. So for sine of x is equal to a half, we know we can have y at a half for x is equal to pi over 6. And I just remembered that I have a circle tool in Photoshop that I can use to not have to draw horrible circles anymore. So honestly, this is not a perfect coordinate system, but when we did this, we had, say here was pi over 6, we would draw a reference to another angle that gave us half. This was pi over 6, and we would get that the other possibility for y equaling a half is at 5 pi over 6, so x can equal pi over 6, or x can equal 5 pi over 6. We can do the same exact thing even if we have a coefficient or whatever have you on the inside. So cosine of 2x is equal to a half on 0 to 2 pi. So again, I'm still looking for values. In this case, cosine is my x coordinate. So when x is equal to a half. This happens at pi over 3. And remember, x is positive in quadrants 1 and 4. So we want to do symmetry of the x-axis to get the other answer as 5 pi over 3. Okay. So you're saying, but what about the 2x? Well, the 2x we just bring down and say 2x is equal to pi over 3. Or 2x is equal to 5 pi over 3. And then from here, we would just go and we would divide by 2. So we get x is equal to pi over 6. or x is equal to 5 pi over 6. Okay, that's great. So we have two solutions, but 5 pi over 6 is less than pi, which is equal to 6 pi over 6. So we haven't actually covered our full period. So we're actually going to have more answers than just pi over 6 and 5 pi over 6 because of the coefficient 2, which represents our period. So in reality, we're actually going to be looking for this to be over 0 to 4 pi. Because this 2 tells me I complete 2 full passes around the circle in the matter of 2 pi. I'm going twice as fast in my graph. Alright, so in order to find our other two solutions, I'm going to underline the 2 and there, and make sure I have the R over. So to find our other solutions, we need to know coterminal angles. They're still going to be the same line within a normal unit circle, so over the period of 0 to 2 pi. I just now want to find 4 angles really instead of 2, since I'm repeating this twice. So to find a coterminal angle, we just add 2 pi. So 2x is equal to pi over 3 plus 2 pi. Oop, not 2x. Or 2x is equal to 5 pi over 3 plus 2 pi. Okay. 2 pi is 6 pi over 3. So 2x is equal to 7 pi over 3. I'm going to write that down. Or 2x is equal to 11 pi over 3. Then we still just divide by 2 or multiply by half. And then we also get 2 more answers as x is equal to 7 pi over 6 or x is equal to 11 pi over 6. I'll write my 11 bigger. So in this case, since our period would normally be, so to find our period, this would be our b value. We would do period is equal to 2 pi over b. So this is equal to 2 pi over 2, which is equal to pi. So since we're completing 2 periods in the normal amount of 2 pi, we're going to have twice the number of answers, which are pi over 6, or twice the number of solutions. 5 pi over 6. This is 7 pi over 6. And 11 pi over 6. If we look at these particular answers, pi over 6 is in quadrant 1, 5 pi over 6 is in quadrant 2, 7 pi over 6 is in quadrant 3, 11 pi over 6 would be in quadrant 4. So we have not gone further than 1 unit circle. Okay, let's look at another example like this. I'm going to do this in blank. So if we have sine of 2x equal to a half over 0 to 2 pi, well, in this case, again, the period of our function is actually 2 pi over 2, which is equal to pi. So we're going to be completing 2 periods within the normal unit circle. So we're going to have twice as many solutions, since this will give us 2 solutions. So for sine of x, usually we have half at pi over 6, or, well, we need quadrant 1, so this would be, sorry, quadrant 2, this would be 5 pi over 6. This is one we actually did earlier before. So in this case, we're going to get x is equal to pi over 12, or x is equal to 5 pi over 12. That's just from dividing by 2. Now, we have not completed even a full period yet. 5 pi over 12 is less than pi, so we haven't even finished a full unit circle. So I need to find reference angles. I'm going to do this in blue, green. So I got 2x. To find reference angles, I take my angle and add 2 pi, because I know I'm completing 2 circles, so I'm actually going to hit pi over 6 twice. I would have started going around, I'd hit pi over 6, I'd go all the way around, I'd hit 5 pi over 6, I'd keep going around, I'm now going 2 pi, I'd hit pi over 6 again, but this is actually now plus 2 pi. And then I'd go around and around and around and around, and hit 5 pi over 6 again, but adding 2 pi. And then complete 2 periods. The other option is, well, we saw it, so this is going to be 5 pi over 6 plus 2 pi. 2 pi is 12 pi over 6. So I have 2x is equal to 13 pi over 6, or 2x is equal to 17 pi over 6. In this case, we just divide by 2. We're going to get x is equal to 13 pi over 12, or x is equal to 17 pi over 12. So in this case, our 4 solutions, since we are hitting pi over 6 and 5 pi over 6 twice in our unit circle, our 4 solutions are pi over 12, 5 pi over 12, 13 pi over 12, and 17 pi over 12. If this was, say, a 3, we'd actually end up having 6 solutions, because then I'd hit pi over 6 3 times. I'd hit 5 pi over 6 3 times. So essentially this is going to be how many times you multiply your number of solutions by, because it tells you how many times you hit those angles that give you half. So then, if you need to pause, you always can take more notes. We may not always be given an interval, and we kind of just practice this with finding coterminal angles. So we saw to be able to find a coterminal angle, we would do theta, and we would add 2 pi. So this is how we would find one coterminal angle. If I wanted to find a second coterminal angle, I could do theta plus 4 pi, or theta plus 6 pi. So every time, well, 4 is equal to 2 times 2 pi, 6 is equal to 2 times 3 pi. So to find any coterminal angle, I could do theta plus 2 times some integer times pi. N is an integer. Okay. So if I were to give you a problem such as sine of x is equal to root 3 over 2, but not give you an interval, so there's no interval, you should approach these by one, finding solutions as if, so find solutions as if interval is 0 to 2 pi. In this case, sine of x is equal to root 3 over 2. When x is equal to, this would be pi over 3, and x is equal to, I would need 2 pi over 3. So these come from our unit circle. Okay, so these are solutions for if our interval was 0 to 2 pi. Our second step is to add in, I'm going to go underline this in green, so add in the repetition. So in this case, my solutions would be x is equal to pi over 3 plus 2n pi, or x is equal to 2 pi over 3 plus 2n pi. Now remember, n can be 0. 0 is an integer. So this could be 2 pi over 3 plus 0, which gives us our original solution. This would change for tangent. So the period of, say, tangent is not actually 2 pi. So for tangent, cotangent, cosecant, and secant, your period would be reduced to just regular pi. So you'd only be adding n pi. So we're going to now actually do a problem with tangent. So we're going to solve tan of 2x is equal to root 3. Negative root 3. Okay. We know tangent is represented as y over x. We know that x is equal to 0 at pi over 2 and 3 pi over 2. 3 pi over 2 minus pi over 2 is 2 pi over 2, which is equal to pi, so that's why our period is just pi. Because we have asymptotes at anything that's pi over 2 or anything that's 3 pi over 2, so any intervals of those. Next, we need to figure out when tangent is equal to negative root 3 over 2, so that we know what angles 2x can equal. We're kind of limited actually to the number we could have. We know tangent is positive in quadrants 1 and 3. So we write positive in Q1, comma Q3. So our two angles are going to come from quadrant 2 and quadrant 4. We know tangent, again, is y over x. We know we need a root 3. I'm going to kind of cheat a little bit, though if you want to pause right now, I would say pause and try and figure out which angles it would be. The actual solutions would be, well, we need a root 3 in the numerator. We have root 3 alone, so what I'm going to do is use y as root 3 over 2, x as a half, and I'm just showing us the form right now. I'm not worried about the negative. The negative will come into play based on the quadrants. So this would be times 2 over 1 times 2 over 1. So here we cancel out everything in the denominator of the double fraction. And for this, our 2's cancel out. So we just showed that we need wherever y would be root 3 over 2 or negative root 3 over 2, and x would be a half. So this occurs at, well, my first one in quadrant 2 comes from 2 pi over 3. and write q2. Or 2x is equal to, this one would be 5 pi over 3. Now, I could actually stop us here to show something, but I'm going to come back to it afterwards. So currently I have 2x is 2 pi over 3, and 2x is 5 pi over 3. If I divide by, I'm going to write these in red, just because these are not correct, technically. This is the wrong way to do it. I made a horrible mistake. I have to go back. First. I missed my n. And I turned this into 3 over 3, and then I just got rid of the n. So it was awkward that I had 5 pi over 3. I need to have 5 pi n over 3. Nope. Right. I'm really not doing well right now. I just forgot to record an entirely correct section. So if this seems super split up, it's because I keep making mistakes and recording. So we can do this really, I'm going to start doing this the wrong way, which is how we might normally approach it. So the first solution could be 2x for repetition is equal to 2 pi. Remember, the period is only pi, so this is just n pi. The other solution would be 2x is equal to 5 pi over 3 plus n pi. I need common denominators, so you have 2x is equal to 2 pi over 3 plus 3n pi over 3, or 2x is equal to 5 pi over 3 plus 3n pi over 3. Okay. From here, we can then combine our fractions. So we have 2x is equal to 2 pi plus 3n pi over 3. 2x is equal to 5 pi plus 3n pi over 3. So x is equal to 2 pi plus 3n pi over 6, or x is equal to 5 pi plus 3n pi over 6. So this was incorrect then. I did something wrong here, which means we have to go back to the consideration of our period. The period is just pi. I've discussed quadrants 1, 2, 3, and 4, which means I've actually considered a period of 2 pi, so I don't need quadrants 3 or 4 for this problem, since tangent only has a period of pi. And we're going to see why this is true coming up. So I only have this one solution. So I got 2x is equal to 2 pi over 3 plus n pi. Now, I'm not going to do anything crazy right now. I'm just going to divide by 2 to get x is equal to 2 divided by 2 cancels. So this is pi over 3 plus n pi over 2. Now let's plug in, I don't know, say 1. I want to show us this form. So I'm going to leave this in terms of 2x. So 2x is equal to 2 pi over 3 plus pi. Well, pi is 3 pi over 3. So 2x is equal to 2 pi over 3 plus 3 pi over 3. But now we can combine these and we get 2x is equal to 5 pi over 3, which is what we had. So this solution, when we make this the repetitive or periodic solution, already covers 5 pi over 3. So if our period is pi, well, we've reduced our period for tangent, so we only actually care about 2 quadrants. So we only get, in this case, 1 solution. This is different from before. So this is different from like the sine and cosine example because of the fact, so over here we had sine of 2x equals a half, and then we actually had 4 solutions. Well, this is different because our period for sine is 2 pi. Our period for tangent is just pi. So we're going to have less solutions for tangent. Okay, so that actually concludes today's video. So tomorrow we're going to be continuing. Again, please, if you haven't already taken some time to review the unit circle and different methods, just search up different methods for remembering the unit circle. I'm going to post some that I can find a little bit later. I might put them in the comments of this video, actually. That would probably be smarter. So take some time to work with that. You want that to be kind of something you're comfortable with. However you come to memorize it is how you memorize it. I've done different tricks over the years. When I learned it, we learned it brute force. Just know the numbers. We didn't learn any tricks. So like the sign increasing trick that I have mentioned in class is something I came up with while I was brute forcing it. I was like, oh, hey, look, sign is increasing. It's got the in it. Tomorrow and Wednesday, we'll be doing content of 6.6. This is 6.6, right? Yeah, this is 6.6. So we're doing more content with those. Thursday will be like a review day kind of for a test, but it'll be focused on 6.6. But that uses all of the material throughout the section, or the unit. And then Friday, you'll be given the test to start. So again, tomorrow and Wednesday, we have a noon conference. Thursday, just office hours. Friday, a test on your own. So there won't be office hours Friday or Monday when it's due. All right, have a good one.